In this lesson on the structure of matter, we're going to look at describing that protons and electrons are not elementary particles since they consist of quarks. But let's first talk about what is a fundamental particle. In particle physics, a fundamental particle or an elementary particle is a subatomic particle that is not composed of other particles. Over the next few months, we are going to study the standard model of particle physics or elementary particles in greater detail. And this particular theoretical framework has taken many decades of experimental endeavors in the 20th century in order to be able to prove. And while we're not going to go into detail at present, I would like to show you the basic structure of it. So if we look at right at the top, there are elementary particles, and then we see on the one side there are elementary fermions, which obey the Fermi-Dirac statistics that we will talk about later on. And we are going to look at quarks and antiquarks, leptons and antileptons. When we talk about antiquarks and antileptons, we are referring to antimatter. Then on the other side, we have what they refer to as elementary bosons. And bosons are particles that behave according to the Bose-Einstein statistical framework. And within that classification, we have gauge bosons and we have scalar bosons, and we will look at these as well. But before we can do that, we need to start off with that which we know. So at this stage in your journey in physics, you should know that atoms are made up of a nucleus, which consists of neutrons and protons, which are very much heavier than the electrons that whip around the nucleus in energy shells and energy subshells or orbitals. Now, the idea of quarks was proposed initially in the 1960s by Murray Gell-Mann and George Zweig independently. And quarks are weird. The idea of quarks was laughed at by many people in the scientific community until experimental evidence was actually proved that they existed. In essence, there are 6 types or flavors of quarks, and they are the up or the U quark, the down or the D quark, the strange or the S quark, and the very fact that there's a quark called strange, that says it all. A charmed quark or the C quark, the bottom quark or the B quark, and the top quark or the T quark. And each of these quarks has an antimatter partner or an anti-quark, and they are represented, the antiparticles are represented with a bar or a horizontal line on the top. When we learnt about electrons, we were taught that they have a half integral spin, and that 2 electrons in the same orbital have to spin in opposite directions. Now, the idea of spin is a strange one. It comes out of solving the Schrödinger equation, and it's linked to the magnetic dipole moment of particles. And albeit that it is not completely like classical spin, it's not like classical spin, we can understand it as a plus spin, plus half spin, and a minus half spin or a negative half spin, that these particles are spinning in opposite directions. So all quarks have a half integral spin. We use the letter S in quantum mechanics to represent spin, and they have a half spin. They can be, with electrons, it can be plus a half or a negative half, and that is the case with all fermions. We call particles who have a half integral spin fermions because they behave according to a theoretical framework that is referred to as Fermi-Dirac statistics. And Fermi-Dirac statistics works for particles that have spins of a half or 3/2, and we're not going to do this in great detail in the course. The Fermi-Dirac statistics and the Bose-Einstein statistics is something you will encounter later on in your university studies when you do statistical mechanics. The most radical proposal was that quarks have a fractional charge. Now, this has never been observed, but it was proposed that they have plus or minus or negative 2/3 the charge of an electron, or plus or minus 1/3 the charge of an electron. And we should know that the magnitude of the charge of an electron is 1,619 times 10 to the negative 19 coulombs. We know that it's actually negative 1,619 times 10 to the negative 19 coulombs, and that of a proton is positive 1,6 times 10 to the negative 19 coulombs. Now, this concept of a plus 2/3 or a 1/3 of the charge of an electron was an extremely strange concept, but we will see that it actually makes sense later on. So let's first look at the up quark in detail. So the up quark, represented by U, has a spin 1/2, as do all of the 6 flavors of quarks. The plus 2/3 of a charge of an electron we represent just as plus 2/3, much the same as we represent the charge on a proton sometimes as plus 1 and the charge on an electron as negative 1. We are using a relative description there, where we are using the base charge is that of the magnitude of the charge of an electron. The mass of an up quark is 0,005 giga electron volts per the speed of light squared. Now, this is a strange unit for mass, and we're going to explain this in more detail. In particle physics, we use the electron volt as the fundamental unit for energy. So let's first start by explaining this. So let's assume that we have the following experimental setup, where we have 2 metal plates that are charged by a 1 volt battery or cell, and this one is a negative electrode and this one will be a positive electrode. So on here there will be an excess of electrons, and here there will be an excess of protons and a depletion of electrons. So this 1 volt power supply is then creating a potential difference across here, which is going to result in an electric field, an E field, that according to convention will run from right to left, because we define the direction of the electric field as the direction in which positive charge would flow under the influence of the electric field. Now, an electric field, like a gravitational field, applies a force on a particular entity. So gravitational fields apply force on masses, and so the field strength of a gravitational field would be the force of gravity applied to an object per the mass of the object. Now, in the case of an electric field, the electric field strength is the force applied, the electrostatic force or the electric force applied per unit charge. Now, electrons are negative, and if there are an excess of electrons on this plate, then electrons will be pulled across here to the positive plate by means of the E field or the electric field. And electrons are negative, so they'll be repelled here and attracted there. The question is, how much energy will a single electron gain when it moves from this negatively charged electrode, or the cathode, all the way across under the influence of the electric field to the positive cathode or anode? Well, we start off with the fundamental definition of voltage, and that is the work done, or the net work done, on charge per unit charge. And so by rearranging our formula for the voltage so that the W net is the subject of the formula, we get that W net is equal to the voltage multiplied by the charge of the electron, which is the charge under the influence of the electric field. Now, bringing in something called the work energy theorem, which states that the net work done on an object by an agent is equal to the change in kinetic energy of the object under the influence of the agent, we are then able to get that the voltage multiplied by the charge of the electron is equal to the change in kinetic energy of the electron. So in the context of this electric field, the net work done by the electric field, by the force of the electric field on the electron, is going to result in the change in kinetic energy. So the initial kinetic energy of the electron here as it leaves the surface will be 0, and when it reaches here, it's going to be a maximum value, because that will be the maximum voltage, because this electric field is going to accelerate this electron. So if we now say the voltage is 1 volt, which it is across here, because the voltage across the plates is 1 volt due to the external power source, and the charge is 1e, where we use E as the magnitude, as a symbol for the magnitude of the electron's charge, then the delta Ek is the change in kinetic energy, Ek final minus Ek initial. Then on the left-hand side, we see that the 1 volt multiplied by 1 electron can be written as 1 electron volt. So that is a unit of energy, because we can see on the right-hand side, that's the kinetic energy. Now, 1 volt is 1 joule per coulomb. So that is the base unit, the base units that make up the volt. You can see a voltage is work or energy over charge, so it's joules over coulombs. So 1 volt is 1 joule per coulomb, and the fundamental charge, the electron's charge, is 1.6 or 1,6 times 10 to the negative 19 coulombs. As I've mentioned before, if we assume that the electron starts with a 0 velocity, which is probably not strictly true, because even though the electron was in the surface, it would still be vibrating and moving around. But let's assume, let's define the kinetic energy of the electron at that point there, then the maximum kinetic energy will be there. Then we can say that the maximum kinetic energy would be 1 electron volt. In a way, we can also just say that that's the change in the kinetic energy. So this here is just used to make it mathematically simpler, but it's not really that important in this context. The important thing is that when the electron starts and being under the influence of the electric field, and when it reaches there, the difference in energy, the energy that it's gained, will be 1 electron volt, which is equivalent to 1,6 times 10 to the negative 19 joules. Now, the way to remember that is that in essence, 1 electron volt has the same magnitude as the charge of an electron, which is 1.6 times 10 to the negative 19 joules. But because it's a unit of energy, its unit is not coulombs, which is a unit for charge, but joules. And so we are now going to use this going forward to explain where that unit gigaelectron volts per c squared comes from. So prefixes are very important in physics. So let's just revise. 1 kilo electron volt will be equal to 10 to the 3 electron volts, or 1,000 electron volts. Remember, the prefix kilo means 1,000. The prefix capital M stands for mega, and mega is 10 to the 6, or a million. So 1 mega electron volt will be equal to 10 to the 6 electron volts, or a million electron volts. Therefore, 1 giga electron volt will equal 10 to the 9 electron volts, or a billion electron volts. And 1 tera electron volt is equal to 10 to the 12 electron volts, which is a trillion electron volts. Undoubtedly, the most famous and best known formula in physics is the energy equals mass times speed of light squared formula from Einstein's theory of special relativity. So if we take E equals mc squared and we rearrange it so that m is the subject of the formula, then we get that energy over the speed of light squared equals the mass. And this is where the unit electron volt over the speed of light squared comes from. Now, the speed of light is 3 times 10 to the 8 meters per second. So the speed of light squared is 3 times 10 to the 8 times 3 times 10 to the 8, which gives us 9 times 10 to the 16, which is a huge number. So we are obviously dealing with extremely small masses, because if you take the energy and divide it by that massive, that monstrous number, you are invariably going to get a very small value in kilograms. Now that we've explained what the electron volt per c squared unit means, we can now go further and say that the mass of the up quark is equal to 0.05 times 10 to the 9 electron volts per c squared, because giga is equivalent to a billion, or times 10 to the 9. And then an electron volt is 1,6 times 10 to the negative 19 joules, because that's the unit of energy that we use in particle physics. And c squared, as I've mentioned, is 3 times 10 to the 8 meters per second squared. And so we get a extremely tiny mass in kilograms. So this is the mass of an up quark, which is approximately 8,889 times 10 to the negative 30 kilograms. Now, if we look at the standard mass for an electron, which is 9,11 times 10 to the minus 31 kilograms, we see that quarks are of the same similar order of magnitude when it comes to mass as that of electrons. Looking at the down quark also has a spin a half, but its fractional charge is negative 1/3 that of an electron, or negative 1/3. Its mass is heavier, 0.008 gigaelectron volts per c squared, which then means that its mass is 14,222 times 10 to the minus 30 kilograms. So immediately we see that there are quarks that have different masses, and this becomes extremely important when it comes to explaining why the neutron and the proton, albeit that they're both in the nucleus, have got slightly different total masses. Using the quark model to explain the internal structure of the proton, we can represent it as follows. We can represent the extent of the proton as a sphere, and inside this proton there are 2 up quarks and 1 down quark, which are attracted to each other by the strong nuclear force, which is an extremely strong non-contact force. We can think of the force as extremely strong springs that pull the quarks toward each other. So if we want to pull a quark away from the other quarks, then the spring of the strong nuclear force is going to pull it back. The total spin of a proton is +1/2, and hence this is why it, like an electron, is classified as a fermion. And we can explain the total spin as being 1/2 by looking at the spins of the component quarks. So in the case of this proton, there are 2 up quarks. Each of them have a spin of +1/2. We can call it an up spin. So each of them has a +1/2 spin, and the down quark has a down spin, or a -1/2. And so together they add up to 1/2, which implies it's a fermion. If we look at the total charge, each of the up quarks has a charge of +2/3. Remember, that's +2/3 the magnitude of the charge of an electron. And the down quark has a -1/3 charge, and so that adds up to 3/3, which is +1. And keep in mind that the +1 is 1 times the magnitude of the charge of an electron, and we know that a proton has the same magnitude charge as an electron does, but just positive. So plus 1 represents plus 1,6 times 10 to the negative 19 coulombs. Now we consider a neutron, and we see that with a neutron it consists of an up quark and 2 down quarks. The total spin is going to be negative a half for the up quark and plus a half for the 2 down quarks, which also gives us plus a half for the total spin of a neutron. We also look then at the total charge. The total charge is plus 2/3 for an up quark, minus a third for each of the down quarks, which gives us a total charge of 0, and we know that the neutron is neutral. So the quark model also goes to explain why the mass of a neutron is actually greater than the mass of a proton. And this has been determined experimentally because of the fact that down quarks are heavier than up quarks, and in the case of a proton it consists of 2 up quarks which are lighter than the 1 down quark, but in the case of a neutron there are 2 heavier down quarks and 1 lighter up quark, and therefore it is heavier. So the quark model explains why protons are positive and neutrons are neutral. And as I've mentioned, it also explains why neutrons are slightly heavier than protons. We can see here that the mass of a proton is 938,272 mega electron volts per speed of light squared, which amounts to 1,672 times 10 to the minus 27 kilograms, whereas the mass of a neutron is 939,565 mega electron volts per speed of light squared, which is equal to 1,674 times 10 to the minus 27 kilograms. So, albeit that there is a very small difference between the neutrons and the protons, the quark model still explains it in a very effective manner. But like with any theory, there are positives and then there are also negatives. So one of the negatives of the theory is that it seems to, on the surface, break Pauli's exclusion principle. So Pauli's exclusion principle is a fundamental principle in quantum mechanics. It's one that we've actually encountered before when we did Aufbau diagrams in grade 10, where we learned that within a orbital, whether it be an s orbital or a p orbital, your electrons need to have opposite spins in order to satisfy Pauli's exclusion principle. A more extensive definition of Pauli's exclusion principle, or statement of it, is that 2 or more identical fermions cannot occupy the same quantum state in the same quantum system simultaneously. So what that means is that when you have got a set of quantum numbers that explain the state of a fermion, for instance, n being the principal quantum number, for instance, if the electron fermion appears in energy level 2, then n would equal 2. That would be the principal quantum number. The spin is another one. The set of quantum numbers cannot be the same for fermions that are in the same quantum state. So in the case of quarks, we see that with protons, we had 2 of the quarks having the same spin, and in the case of neutrons, 2 of the quarks having the same spin as well. So that must mean that there's another type of quantum number that we have not yet considered, because if these were the only quantum numbers, well, then it would be breaking Pauli's exclusion principle. So this leads us to the introduction of another quantum number, namely color. But before we go into the details of color, we are going to just take a few minutes to delve into the experimental evidence for quarks, because quarks seem very weird and they seem to a lot of people to basically be just a hypothetical particle that could not be found directly, proven directly, experimentally. It had a theory that seemed to explain certain things like the difference in mass between a proton and a neutron, explaining why a neutron is neutral and a proton is positive. But to many scientists, they basically seem to be mathematical curiosities. A free quark had never been observed and still has never been observed directly. So this obviously has cast a lot of doubt over the quark model for many years. However, in 1967 at SLAC, which is the Stanford Linear Accelerator Center in America, where they were scattering 20 giga-electron-volt electrons from protons, they produced results like the Rutherford experiment had obtained from the nucleus 60 years ago. So what they were doing is they were firing high energy electrons into protons, and the result was that there was scattering that led to them believe that there was an internal structure to the protons. So the results of the SLAC scattering experiment showed that there are 3 point-like particles, and these particles all have diameters much smaller than the probing wavelength. So they were firing these electrons, high energy electrons, through the proton, and they found that some of the electrons scattered in certain directions, which when they processed the data, it pointed to the fact that the scattering patterns were the result of 3 point-like particles inside the proton. So let's just talk a little bit about probing wavelength. So when you're firing a radiation that has a specific wavelength, so in the case of an electron, we know that electrons are particles, but they're also waves. So the energy in quantum mechanics is equal to h Planck's constant times the frequency, but frequency is c over lambda, lambda being the wavelength, c being the speed of light. So the energy of a quantum particle is equal to h times c over the wavelength. Now if we rearrange this, the wavelength is equal to Planck's constant multiplied by the speed of light squared divided by the energy of that particular photon of that radiation. Now, if we substitute Planck's constant in place of h, 6,63 times 10 to the minus 34 joules seconds. The speed of light is 3 times 10 to the 8 meters per second. These are both physical constants that don't vary. If we now take 20 giga-electron volts, 20 times 10 to the 9 is 20 giga-electron volts, is 1.6 times 10 to the minus 19 joules per electron volt. We get that the probing wavelength is 6,216 times 10 to the minus 17 meters, which implies that the diameter of a quark must be less than 6,216 times 10 to the minus 17 meters in order to scatter that particular radiation. More recent high-energy experiments have produced jets of particles in collisions, and this implies that 3 particles exist inside the nucleons being the neutrons and the protons. So, for instance, at the Alice detector at CERN, where the Large Hadron Collider is to be found, where they collide protons in batches so that you get proton-proton collisions, and they fire these protons in the Large Hadron Collider so that each proton has 7 tera-electron volts, so the collision between 2 protons of 7 tera-electron volts is in effect 14 tera-electron volts. Then there is a conversion of the energies into specific particles, and what they found here is that there were jets of particles that were coming out of these collisions. So individual quarks are not able to be separated from each other no matter how much energy is in the system. This is an experimental fact. No matter how much energy one puts into the system, one never gets an individual quark on its own, isolated. These quarks are confined in the nucleon. It's as if the strong nuclear force is like infinitely strong springs, so that the more you pull the quarks away from each other, the more the spring pulls back, so you can never separate a quark from the other quarks in the system. The energy separating the quarks only pulls them so far apart before it starts to be converted into other particles. And so, with the conservation of momentum being a fundamental conservation law, it requires that the particles come out in jets along the 3 paths in which the quarks were being pulled, and this is exactly what they observed. So this, together with the scattering experiments of the 20 mega electron volt electrons being fired into the proton, this is another proof of the fact that there are 3 quarks inside protons and neutrons. So now that we have conclusive evidence of the fact that there are quarks and that 3 quarks make up neutrons and protons, we can now go back to what we stated earlier, that there must be another type of quantum number, namely color. Now this color is not like the color of visible light. This is not really red, orange, yellow, green, blue, indigo, violet. This is a model that follows similarities. It's analogous to real light, but it's not real light. Much the same as spin in quantum mechanics is not quite this way we classically interpret spin, but we use it nonetheless effectively, and it works. So the way this quantum number works is according to rules that are analogous to the 3 primary and 3 secondary colors. It's weird, but it's a good model because it works. So here goes. A quark can have one of 3 values, 3 color values. We call them red, green, blue, primary colors, RGB. And antiquarks have 3 color values we call anti-red, which is R bar or cyan, anti-green, G bar or magenta, and anti-blue, which is B bar or yellow. So we have the color values for quarks and the color values for antiquarks. So let's look at the rules of color addition. So we have 3 primary colors, red, green, blue, and just like with visible light, when red and green are mixed, you get yellow. When red and blue are mixed, you get magenta. And when green and blue are mixed, you get cyan. When all 3 are mixed, we then get white. So when you have red plus green plus blue, or RGB, we get white. Yellow is RG, red and green. Magenta is red and blue, RB. Cyan is blue and green, or BG. These are the secondary colors. So this implies that anti-blue, right, would be yellow, which comprises of red and green. And that anti-green, that which is not green, right, is going to be magenta, which is red and blue. And that anti-red, that which is not red, is going to be cyan, which is a mixture of blue and green. So these are the anti-quark colors, and these are the quark colors, the primary colors. So let's apply this now to hadrons. Now, we're going to learn more about hadrons and more about the classification of elementary particles later on, but for the time being, we can define hadrons as particles that are made up of quarks. Now, you get 2 basic types of hadrons. You get baryons and you get mesons. So thus far, we've worked with baryons. So baryons are particles that consist of 3 quarks, and we've dealt with protons and with neutrons, each consisting of 3 quarks. Now, when it comes to color, the quarks need to have 3 different primary colors that add up to white. So if we look here at this baryon, and this baryon could be a neutron or a proton, if we look here, over and above the spin, each of the quarks must have a different quantum number of color. And so this is where now Pauli's exclusion principle is satisfied, that even if these 2 quarks have the same spin and they have other quantum numbers, like for instance n, the primary quantum number, the fact that they have different colors means that they don't have the same set of quantum numbers in the same quantum state. So they're in this quantum state, namely the baryon, but the red and the green and the blue means that each of them have got different color quantum numbers. But what's important is that the colors, the quantum colors, must add up to white. So baryons must always have 3 quarks with the 3 different primary colors, red, green, blue, to produce white in between there. I want to stipulate again that this is not real colors. It's not like the quarks are red or blue or green. Those colors are the colors, those colors when we refer to light are in the 390 to 780 nanometer range. All right, that's about 700, let's say 500, on average 500 times 10 to the minus 9 meters, which would make it around 10 to the minus 7 meters. Now think about the diameter of a quark. We see the diameter of a quark is of the order of magnitude 10 to the minus 17 meters. So quarks are way, 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 way smaller than what the wavelengths of light are. So there's no way that there is a direct association with real colors. It's just a model that we use. So now if we go to mesons we'll still learn more about. Mesons consist of two quarks, and these 2 quarks must also have color numbers that add up to white. So a meson invariably consists of a quark and an antiquark. So if this one is red, this one's going to be anti-red. Now, if we look at the possibilities, we can have quarks that have red and anti-red, or green and anti-green, or blue and anti-blue. And those combinations need to be the combinations of the quantum numbers for color in order to satisfy the rule that the total colors, the color addition, we're talking quantum color now, must add up to white for baryons and for mesons. So if we look in more detail here, we see that if we've got red and anti-red equals red, and remember anti-red is cyan, but cyan is blue and green, and red, blue and green is white. If we had a meson that had green and anti-green, then it would be green and anti-green is magenta, and magenta is red and blue. Once again, red, green, blue gives us white. If we had a meson with blue and anti-blue, anti-blue is yellow, yellow is red and green, so once again, red, blue and green, which is white. So mesons must always produce a net white color when it comes to addition of quantum numbers. So now when you take quark theory and the addition of color as another quantum number, then we land up with quantum chromodynamics. Chromos is the Greek word for color. Think of chromatography. In grade 8, we do chromatography as a method of separation of a pigment into different pigments, or let's say, for instance, an ink into different pigments. Okay, chromo means color. So quantum chromodynamics means it's a theory of quarks where there is an element of color involved, and the color is not real color. The color is another type of quantum number. And so quantum chromodynamics is known in physics as QCD, quantum chromodynamics, as opposed to QED, which is quantum electrodynamics, which Richard Feynman became famous for. He won the Nobel Prize for QED. QED is to do with the way photons, electromagnetic radiation, interacts with light. QCD is about how quarks can be used to explain the internal structure of protons, neutrons, and mesons. So now coming back to the internal structure of the proton, remember we said there was a problem with the fact that these 2 up quarks would have the same spin in this quantum system, but now if we introduce color, and now we have red, blue, and green, we see that these 2 up quarks, although they both have a spin, a positive or half spin, the quantum color numbers differ, and the RBG produces white, so it satisfies the law of color addition when it comes to adding quantum numbers, the quantum color numbers. So now looking at the neutron, we can see that here too, even though these 2 down quarks have both got the same spin, Pauli's exclusion principle is still satisfied because each of the quarks has got a different quantum color number, and these quantum color numbers, red, blue, green, add up to white, so that satisfies the rules of color addition. And so now we have a theory to explain the internal structure of protons and neutrons and mesons, which falls directly in line with experimental evidence not only of quarks, but of certain quantities of neutrons and protons, like for instance their charge, like for instance their differences in mass. And so this is a very, very powerful theory which we can now use and move forward to look at other elementary particles, as well as looking at radioactivity and other nuclear processes, and this will enable us to understand these phenomena on a deeper level.